we can now obtain the minimum mean squared error solution of this matrix multiplication using the so-called Moore-Penrose Pseudo inverse. So here in Wikipedia you can read about the Moore-Penrose inverse, so you can understand what's going on. Thus this pseudo inverse defines the column vector h of t transposed, which minimizes the distance to a given x with the matrix A, which contains our signal to be filtered. So A times h of w transposed will imply to x of t transpose. So matrix A and vector x are known. This is done in a training phase to obtain the Wiener filter coefficients from noisy signals in matrix A and clean signals in vector x. And vector h of w is unknown at the moment. After the training phase, the filter can also be applied to similar signals. So this problem can be solved exactly if the matrix A is a square and invertible. Just multiplying the equation with A to the power of minus 1 from the left would give us the solution. So now we have here the h of w is equal to A inverse times x of t. This cannot be done if A is non-square. For instance, if it has more rows than columns. In this case, we don't have an exact solution, but many solutions that come close to x. We would like to obtain the solution which comes closest to x in a mean squared error distance sense. So this is also called the Euclidean distance. So this solution is derived using the pseudo inverse. So we have A transpose times A times h of w transposed equals to A transposed times x transposed. So here A transpose times A is now a square matrix and usually invertible, such that we obtain our solution h w transpose is equal to A transpose times A to the power of minus 1 times A transpose times x transpose. So this h of w is now the solution we were looking for, and this solution has the minimum square distance to the unnoisy version of all solutions.